So in this video I want to talk about separable differential equations and how to separate variables. So what a separable differential equation is an equation of the form dy over dx is equal to some constant k multiplied by x naught minus a. You need to know this form. You also need to know how to get it into this form. The antiderivative of some function y dy equal to antiderivative of some function x dx. When you get it into this form, you can integrate and then simplify. Separable differential equations are some of the most useful differential equations that you'll come across in physics and engineering. It's probably the most used among physics and engineering. So if you are a physics or engineering student or even an applied mathematics student, you need to get this down. With that being said, I guess let's get into this. I'm going to use this equation here as my example for this video. And first thing you want to do is get it into this form here. So we're going to rewrite this. You need to understand that y prime is the same thing as it's the derivative dy over dx. So we'll start there. Dy over dx equal to 0.01 y minus 2. Now you'll notice this isn't quite in this form yet. We haven't found our constant k. So we need to simplify this part to get it into this form. So what we're going to do is we're going to factor this part of the equation. So we're going to rewrite it again. Dy over dx is equal to, and to simplify this, what we would do is we're going to pull out the 0.01 and we're going to use that as our k. 0.01 multiplied by y minus 200, because 200 multiplied by 0.01 is 2. Now that we have it in this form, we can separate our variables and get it into this form. So we're going to multiply both sides of our equation by dx, and then we're going to divide both sides of our equation by the x naught minus a term, which is this right here, y minus 200. So we get dy divided by y minus 200 is equal to 0.01 dx. And if we integrate both sides, we then get the natural log of y minus 200 is equal to 0.01 x. Now there still isn't a satisfactory solution. We need to get rid of this natural log and we need to isolate y so that it is an actual solution to this differential equation. And I talked about it in the integrating factor videos. To get rid of the natural log, we need to exponentiate both sides. So we get e raised to both sides of our equation. So e raised to the natural log of y minus 200 is equal to, I forgot the plus c right here. I have a bad habit of forgetting my plus c's. Remember the plus c right here. E raised to the natural log of y minus 200 is equal to, the c comes to the front, ce raised to the 0.01x. I do want to write that right here because you're going to see that a lot, and I just kind of touched on it briefly. You need to understand that e raised to some other function, say just ln of x plus c is the same thing as ce raised to the ln x. Whenever you have a plus c in your exponent to e, you can just bring the c down to the front. And right here, you know, the ln and the e cancel, so this is also the same thing as just c times x. But this is really the part I wanted to emphasize because I touched on it very briefly here and in the last video. You need to understand this for this course. But back to this problem. Where was I? Okay, so the ln and the e cancel. So we're left with y minus 200 is equal to ce to 0.01. Oh my goodness gracious, forgive me. X. Now, to isolate y, we just add 200 to both sides. So y is equal to 200 plus ce to the 0.01x. And this is our particular solution for this differential equation.